Hello, welcome to another video on Moocor series. We are continuing our discussion on Module 2. Topic 5 mainly consists of discussions about Big M method. However, before we actually start talking about Big M method, we are going to cover a couple of cases on Simplex method that we covered in Topic 4. First, we are going to look at alternative optimal solutions and see how Simplex method and the optimal tableau will treat these cases. Next, we will be looking at unbounded optimal solutions and how Simplex method treats those and what we can see in the Simplex tableau indicating unbounded solutions. We will also discuss a couple of tie-breaking observations that might be helpful in your calculation. Then we will discuss our main discussion in this topic, which is Big M method. First, let's look at the type of problems that we covered in Topic 4 and give a little bit more information about that format of the problem. Here is an example. This is the type of problem that we covered in Topic 4. You notice that in this problem, which is in the form of a maximization problem, all my constraints are in the form of less than or equal. And all my variables are in the form of greater than or equal 0. This format of the problem is called the canonical form of the LP. And with this canonical form being represented in a matrix format, it would look like this. We are going to cover the matrix notation and the format and all the operations in Topic 7 on Module 3. However, for now, this canonical form is what we are using. The advantage of the canonical form is that the origin is always a feasible extreme point, which would give you immediately two advantages. One, because you have a feasible point, you have a feasible solution. Second, that point is an extreme point, a feasible extreme point. Remember that we said Simplex method requires a feasible extreme point to start with, and then it continues going to adjacent feasible extreme point until it reaches the optimal solution. Canonical form immediately will give us that starting solution. In Topic 5, in Big M method, and in Topic 6, the two-phase method, we deal with the cases that canonical form is not present, which means you may have constraints that are not in the form of less than or equal sign. You may have a constraint that is in the form of equation. You may have a constraint which is in the form of greater than or equal sign. In those cases, we cannot start immediately from the origin. So these two techniques would allow us to start from the origin and then move towards a feasible extreme point. And the moment that we are on a feasible extreme point, then we can continue the regular Simplex method. Now let's start the materials that we are going to cover in Topic 5. Let's start with the case of alternative optimal solution. How would the Simplex tableau show the presence of an alternative optimal solution? Let's start with a two-dimensional LP because we can actually visualize what is going to happen in feasible region. Here is an example, and here is a unique optimal solution for this problem. If we do regular simplex, we would write the problem in standard form. We will identify our basic and non-basic variables. We will start our starting extreme point, and we will perform iterations of the simplex tableau. We're starting with x1 and x2 0, and that's the origin point. From here we would identify entering and leaving variables. This is the second tableau, going through different adjacent extreme points, and we will reach the optimal solution. In this case we had a unique optimal solution. Now let me slightly change the problem. In this case I changed the objective function, and I use the same slope as one of the constraints. Therefore these two will be parallel to each other. When I solve this problem graphically, I will notice that the optimal solution is going to be an alternative optimal solution, is a part of a line. Now let's perform the regular steps of the simplex method. We write the standard form of the problem. We will identify basic and non-basic variables and a starting basic feasible solution x1 0 and x2 0. We will identify entering variable and leaving variables. We would end up at an adjacent extreme point. In this case x2 is an entering variable. We will identify the leaving variable, and we will perform another iteration which will take us to the point that indicates an optimal solution, because there is no negative value in the 0. However, when you look at S1 in this case is a non-basic variable. When you look at S1, you notice that the z value is 0. So it is possible to enter S1 into the basis without changing the value of the objective function. If you perform the iteration, it would actually take you to the other end of the line. The same line that we discussed contains all the same solutions. Again, it is the same story. It is an optimal solution and there is no negative value in the 0. So from that example you can see that alternative solutions, when the tableau indicates the solution is optimal but one or more non-basic variables have the value of 0 in the 0, regular simplex iteration is performed to find the new solution. Optimal value of z will not change, and alternative optimal solutions play significant role in some operations research methods such as goal programming. Now let's look at an example of a problem with unbounded solution, and I have taken a two-variable problem as an example because we can visually see the feasible region and the solution space. In this case we have an unbounded optimal solution. Maximum occurs at infinity. I have written the problem in a standard form, identifying the basic variable, starting again at x1 x2 0, identifying x1 as an entering variable and identifying s1 as a leaving variable. We will perform one iteration of the simplex method. Next tableau indicates that x3 is an entering variable because it has a negative 13 in the 0. However, when I look at the pivot column, there is no positive element in there. Both are negative numbers, which are indicating that you can enter x2 into the basis without causing any problem and take it to of infinity. So unbounded solutions are when Tableau indicates the solution is not optimal, you have negative entries in the zero, but entering pivot column elements are zero or negative. To have an unbounded solution, it is necessary to have an unbounded feasible region, but the reverse is not always true. Let's look at one smart observation which would help us sometimes. In this hypothetical tableau, x4 is an entering variable because it has negative 8. But when I look at x2, which has a small negative value in the 0, I notice that all the pivot columns are negative or 0. Therefore, this indicates an unbounded solution. Here is another one. In this case, I have a tiebreaker, and I can select between x2 and x4, both of them. But when I look at the two pivot column, I notice that if I select x4, I will have an easier set of calculation. Here is another one. In this case, x2 is an entering variable, but I have a tiebreaker for the leaving variable. Which one should I choose? Should I choose 1 as my pivot or 9 as my pivot? Certainly 1 is easier to process. Now there is no guarantee that the result will be faster, but if you have to perform just one iteration, it's better to use those. Now we will start talking about Big M method. We will discuss problem setup, artificial variable, starting solution, legitimizing the tableau, performing iteration. We will also talk about the case when we have no feasible region, and we will make cautions about the magnitude of M. The Big M method. This is a technique which would allow us to address the cases in which the origin is not a feasible extreme point. Let's consider the cases in which we have constraints in the form of greater than or equal or just equal. The problem is that the moment that you introduce a greater than or equal sign constraint, then the slack variable for that constraint becomes in the form of a surplus variable, which is going to be minus some SI value. Here is an example. In this example, you notice that S2 has a negative sign in front of it. Now, if I let x1 through x4 be 0, then S2 will end up to have a negative value, which makes the solution infeasible. The other example is on the third constraint. Notice that the third constraint is an equation itself. So I cannot add another slack variable to it. The purpose of a slack and surplus variable was to make sure that they end up to be an equation. This one, the third one, is already in the form of an equation. So I cannot add any slack or subtract any surplus variable from it. So what would the approach be in these cases? Because remember, the regular simplex method that we introduced in topic 4 required a starting basic feasible solution. A feasible extreme point, and that feasible extreme point for us was the origin. In this case, the origin is out of the question. The origin is an infeasible point. It is an extreme point, but it is an infeasible extreme point. To address these cases, we are introducing a new variable. This variable is called artificial variable. We are going to add artificial variable to our constraints that are in the form of greater than or equal, or in the form of equality, after we convert them into standard form. In the case of greater than or equal, we are going to subtract an S2 in this example, and on the third constraint, no change. After we convert them into standard form, we are going to introduce a new variable called artificial variable. In this case, to the second constraint, I'm introducing an artificial variable. I use the notation of Ri for it, so R1, for example, in this case, for the second one, and R2 for the third one. You may ask the question, by adding a variable to one side of the equation, you are actually changing the balance. And you are correct in making that assumption. So what Simplex method does in either one of these two methods, big M or two-phase, they are going to find a way to make these artificial variables zero. So if at the end you end up with 0 as the value of artificial variables, it looks like you haven't changed anything. And the more important one is that if with anything that you do in these methods, you cannot make these artificial variables 0, that is the point that you can claim that this problem does not have a feasible solution. It does not have a feasible region at all. So in topic 5, we will address it through the big M method. Let's see how big M approaches this problem. For this problem, the three variables S1, R1, and R2 have the proper form to be basic variables. However, this solution of x1, x2, x3, and x4 equals 0 is not a feasible solution. It represents the origin, and origin itself is an infeasible extreme point. To make sure that the artificial variables move toward 0 from the values that they have now, R1 is 5 and R2 is 10, we are going to penalize the objective function if R1 and R2 remain positive. And the way that we do that, we are going to use a very, very large positive value of M multiplied by these artificial variables with a negative coefficient. So we are going to make sure that if R1 and R2 remain positive, the objective function is highly penalized. In terms of standard form, when you take these terms into the left hand side, they become plus MR1 plus MR2 for this specific problem. So having the problem in this form, if we want to create the initial tableau, we have a problem. And that problem is S1 has the condition, but R1 and R2 no longer have the proper form for basic variables because of the presence of R1 and R2 in the objective function row, in the Z row. So we need to try to eliminate these two values from the objective function row. The way that we do it is through row operation. So we can perform row operation and eliminate MR1 and MR2 from the objective function row. For example, we can multiply the second constraint by minus m and add it to the 0. This is the operation performed, and you notice that now the form of the z changes. It becomes involving the values of m itself. We can do the same thing for R2. In this case, we eliminated R1 from the 0. Now we can eliminate R2 from the 0. We will multiply the third constraint in here, which has R2, by negative m, and we will add it to the updated 0. In this case, by doing so, we will eliminate R2 from the objective function row, from the 0. Notice that the final form of the objective function row does not include any R1 and R2. Thus, this objective function row will allow me to introduce S1, R1, and R2 as basic variables into the first tableau of the simplex method. So basically, this is the new form of the problem. I can enter them into my first simplex tableau. The solution is identified. This is not a feasible solution because artificial variables are present in the basis and they are positive. So I'm going to perform the regular simplex tableau operation by identifying entering variable and leaving variable through the min ratio, and in this case R1 is going to be leaving and x3 is going to be entering into the basis. If we perform the operation, our new tableau will indicate that the solution of S1, X3, and R2 is still not feasible because of the presence of R2 in the solution with a positive value. So I will perform another iteration, and in this case R2 happens to be leaving the basis. X2 is entering, so when I perform the regular iteration of the simplex method, I will come up with the new solution. Notice that in here R1 and R2 left the tableau immediately right after each other, but that's not always the case. We are moving toward optimal solution, and in that operation our choice is to find the variable that has the most negative value in there. The new solution is actually feasible, and then now we can talk about the optimality of the solution, which is not optimal because we have negative values in the 0. Performing our operation, x1 enters into the basis, x3 leaves the basis, and the new solution becomes s1, x1, and x2. Again, as I'm looking at the solution, I notice that there is a negative value in the 0 under S2. There I have a negative 7, 6. So S2 becomes my entering variable, X2 becomes my leaving variable, and I will perform the regular simplex method. Notice that there is no more m under the original variable. M only appears under R1 and R2 in the 0. That is an indication that your solution is feasible. So performing the operation, we will end up with the final tableau and the optimal solution, which is feasible and optimal. It is optimal because I don't have any negative values in the 0. Solution of S1 equal 5, X1 equal 10, and S2 equal 15 would lead to the Z value of 30, which is the optimal solution. So let's review the steps. First of all, I wrote the problem in a standard form, added necessary artificial variables to the constraint, penalized the objective function to force artificial variable to become non-basic, and using row operation eliminated artificial variable from 0. And then I performed the simplex iterations. Remember, we started from an infeasible extreme point, which was the origin, and moved through the adjacent extreme points toward the optimal solution. If an optimal solution existed, we would eventually reach it. In that process of moving toward this adjacent extreme point, we will eventually reach a feasible extreme point. Now let's look at a two-variable example. In this case, I have a problem involving two variables and three constraints. Notice that the third constraint in the form of greater than or equals 0. If I plot the feasible region, I notice that origin is no longer a feasible extreme point. So going through the steps, I will write the standard form, then I will set up the problem for the big M by adding artificial variables to the problem and penalizing the objective function, and then we'll perform the row operation to get rid of the artificial variables in the objective function. As I follow these steps and perform the proper operations, I have to multiply the third constraint by negative m and add it to the 0, so the new updated row no longer has the R1 in it. Using the new 0 equation, I can set up the initial tableau of this problem. The initial tableau indicates that S1, S2, and R1 are the solutions, and of course the solution is infeasible because the artificial variable is present with a larger than 0 value. This point represents the origin of the problem. Just performing the regular simplex operations, we will identify the entering variable and leaving variable, and we will perform an iteration of the simplex method. x1 entered and r1 left, the solution becomes feasible. This is the feasible solution, and notice that m only appears under r1 at the 0. So the new solution of s1, s2, and x1 is feasible, but it is not optimal. I will continue performing the operations of the simplex method until I reach a new solution. In this solution of s1, x2, and x1 is still not optimal. It is feasible, but it is not optimal. Notice that the moment that artificial variables leave the basis, they will never come back into the basis. So I will perform another iteration, and this iteration is going to lead to the optimal solution of the problem, and that is s3, x2, and x1, and this solution is optimal. So how do we recognize problems that have no feasible region? How would a simplex tableau show the lack of any feasible solution? Let's look at an example. In this case, again, I made a two-variable problem to be able to plot it, and as I plotted, I noticed that this problem has no feasible solution. So let's follow the steps and set up the first tableau for the big M, and I noticed that the problem is not optimal, so I will continue the process. I will go through the process. I will enter x1 into the basis, and s1 leaves. Now I am faced with a tableau that has no negative value at the 0, but the artificial variable is positive. So when simplex tableau indicates the optimality conditions are satisfied, so no more entering variable can be identified, but at least one artificial variable has a positive value, then LP is infeasible. One additional point: when we are trying to select more negative values in the 0 in the simplex tableau, which one is more negative? Only the sign of the coefficient of m identifies whether a term involving m is positive or negative, regardless of the magnitude of that coefficient. It's the sign of that coefficient that identifies whether a term involving m is positive or negative. In this an exaggerated example, how the terms are positive or negative. When coefficients of m are equal, then the other terms identify whether term involving m is more negative or not. In this case, negative 2m minus 3 is more negative than negative 2m minus 2. Well, I hope that you learned the technique. In topic 6, we are introducing a different approach, and that is two-phase method, while we are discussing the pros and cons of each one of these two techniques. But for now, practice and learn. Thank you very much.